Okay, everyone. So I think we are 5 minutes over now. So what I would like to do is I would like to briefly introduce myself. As you see, we have a big presentation today with a lot of attendees. So thank you, Kaushik, for organizing all the attendees which will join us today. My name is Christian Weidelmeier. I am a physicist at V&F Analyse und Messtechnik GmbH, and we are a manufacturer of multi-component mass spectrometers. Today I'm joined by Siegfried Braun. He is my direct supervisor, and he will assist me today with this meeting. And our main focus today is we want to give you all an overview of one of our instruments that we produce, which is called the HSense. It's an analyzer that is able to measure hydrogen in different scenarios. And our plan for today is we're going to go through a brief presentation to catch you all up to speed what this instrument is good for and how it works. And in the second part of this session, we're going to have a live demonstration on one of the instruments so that you can get a look and also a feel of how this instrument is accessed, let's say on the most basic level via our control software. And we have a small measurement chamber where we can produce different concentrations of hydrogen and measure them with the instrument directly. Okay, so again, welcome. And today we're going to look at an instrument that is built here in-house, which is called the HSense, as it's written here quite predominantly. Contents of these presentations range from typical applications where the measurement of hydrogen is necessary. We have this instrument adapted for different applications. So there is usually two big fields that we service with this instrument, which would be internal combustion engine measurements, and now since the recent years also fuel cell measurements. I see people coming. We're going to go through how the measurement works, how which hardware components are in this instrument. We're going to look over specifications, benefits, and also customer prerequisites which we need to have in order to operate this instrument on site at a customer. So as I've already mentioned, the fields of hydrogen measurement are rather diverse. So this instrument originally was designed at a time where internal combustion engine development was still at a high. So there was always the necessity to have measurements in the exhaust gas of internal combustion engine, and also in the research for catalysts for internal combustion engines. And recently, also in the automotive field, fuel cells, hydrogen fuel cells or PM fuel cells have taken a rise and are a massive field of interest. And since hydrogen is the fuel for these types of fuel cells, the measurement of it is also crucial in order to understand the correct functionality of these fuel cell systems. Apart from automotive, there were also non-automotive fields where we have sold analyzers to. So there were things like exploration of natural hydrogen wells, breath analysis, and also contaminations of hydrogens in other gases. So why would you want to measure hydrogen in internal combustion engines? So historically, this was always a typically linked to the operation of catalyst systems, which are used for after treatment of the exhaust gases. Since hydrogen usually acts as a reductant or even a promoter for some reactions, it was interesting for the people who were developing catalysts to know the exact concentration of hydrogen, which is currently running through their experiment, usually also at different measurement points. And one good example is, for example, SCR catalysts for nitric oxide and nitrogen dioxide emissions. And this was one of their essential parameters to run those experiments. And these have been very well able to be measured with our HSense instrument. And throughout the last years, you could say, PM fuel cells or also other types of fuel cells like SFCs, which can be operated with hydrogen, start to play a more and more crucial role in the energy field. So not just in automotive, but also for power generation and other parts where energy is needed, and where hydrogen is to be established as the crucial fuel, probably of the future, going away from oil and petrol and things like that. And here we have a system which is typically operated on its anode side with 100% hydrogen. So we have collaborated with a few tech companies here in Austria, which have given us something like a spec sheet of what is interesting to them for the fuel cell operation. And we have seen that these fuel cells typically have very, very different sampling conditions on their anode and cathode side. So you'd have one side where you have very high hydrogen concentration on the anode, and typically very low or very short bursts of hydrogen on the cathode side. So we have also developed an HSense instrument with a special gas inlet for this type of application, which I will go through a little bit later in the presentation. And here typically there are two major points. So the hydrogen concentration on the anode side is an important parameter for the operation condition of the fuel cell. And on the cathode side, you typically have like safety issues where you don't want to have certain hydrogen concentrations surpassed, because there is the possibility of explosive mixtures forming. And since on these types of fuel cells, these hydrogen bursts are very short, you need to have an instrument that can react very fast to these hydrogen peaks on the cathode side of the fuel cell. So yeah, this is just, we can also share this presentation later with all of the attendees. The reason why there is hydrogen also on the cathode side is pretty much in the recirculation system of the fuel cell, which is mainly like you don't want to blow off all the fuel that you're not using, but you want to recycle it, which introduces usually a loop on the anode side, which has a so-called bleed valve that can reduce the pressure on the anode side and just blows the hydrogen into the cathode side. And therefore, this valve is has a very short pulse duration, and that will introduce a certain concentration to the cathode side. And the dangerous thing with PM fuel cells is that on the cathode side, there is also lots of oxygen. So the regulations are different, but typically, like scientifically speaking, you have an explosive limit of roughly 5% of hydrogen, which you should not surpass in an ambient air mixture, because then you could have an ignition and therefore an explosive hazard. And people have been interested in measuring these short pulses very much in order to get their safety approbation for their fuel cell systems. Okay, so this graph will show the principal setup of an HSense instrument. So what we would have is we would have the instrument itself. The most basic connection to the instrument always works via an Ethernet connection. So you would have an external computer, you would plug in a network cable to the computer and to the instrument, and then launch the control software on the PC, control the instrument this way. There's also a possibility to have various kinds of interfaces. So here is, for example, there is an AK interface is drawn here, but there is also a possibility to have different kinds of field buses, which can work via Ethernet or which can work via a serial interface like RS-232. Then we would have on the HSense a sample inlet system. So what you would see here is this consists usually of a heated line, some sort of extraction system, which is connected to the combustion engine exhaust in this case. And on the other side, there is also an exhaust system on the HSense. Since we will draw gas from the combustion engine, we'll supply a small amount of it to the measurement cell, and the rest of it will have to be passed through the exhaust system into a safe exhaust ventilation system. The secondary measurement setup is the one that I've talked about regarding PM fuel cells. So since we have two very different sampling points on PM fuel cell systems, so we see it here, we have anode side and we have exhaust or cathode side. This type of HSense instrument is equipped with a double sample inlet. So we would have a sample 1 and a sample 2. So we have, again, for both of these sample inlets, we have heated lines. For the cathode side or exhaust side, we also have something called a heated probe tube. This is due to the very high levels of water and also condensing water that is typically formed on a PM fuel cell. And we have a so-called low gas consumption inlet for the anode side, because any gas measurement technique usually will draw a certain amount of gas from the measurement point. And since the anode side of PM fuel cells are typically running at an elevated pressure, we cannot introduce a very large leak and just take all the gas out from the anode, because this will influence the operation of the fuel cell. So what we have done here is we have designed a special inlet which has a very low gas consumption. So it's always lower than 60 milliliters per minute, even if the anode pressure goes up to 5 bar gauge. And again, we have our HSense instrument. We would have our external PC, and we would have our exhaust system, which of course needs to be connected to some safe way to vent the unused gas into the ambient. So here we have a picture of how the instrument looks like. So this would be the internal combustion engine hydrogen sense. This is also the instrument that we are going to look at later on the live camera. And in comparison, here we have the fuel cell type HSense with the 2 sample inlets. And you see here there are these heated lines, which I've just shown in the schematic. Maybe a little bit what is actually going on in the instrument. So how is the hydrogen measured? The instruments typically consist of 5 major sections. So you would have the sample gas inlet system. This comprises the heated lines. This comprises the gas transfer towards the measurement cell, and also the exhaust venting. The next step would be we would need to have, since we are working with mass spectrometers, so in the vacuum chamber we have an ion source. This is used to ionize the neutral gas molecules into a single positive ion state. The reason why we need this is because we want to influence charged particles in order to do mass analysis. As you might know, ambient air consists mainly of nitrogen, oxygen, and argon. And what we want to measure is hydrogen. Each of these molecules has a different molecular weight. So what we want to see is the mass number 2. This is the mass number for hydrogen, and we don't want to see anything else. And for that, in this instrument, we are using a so-called magnetic sector field, which is able to differentiate between ions of different masses. And once we have selected the mass that we have for hydrogen, which is 2 atomic mass units, we need a particle detector in order to tell us how much hydrogen is actually in the sample. From this particle detector, we will get a signal, which is then worked on by the internal CPU, and then the software will display a concentration value for the amount of hydrogen that has been in the gas sample that we have analyzed. Here's a small schematic of how a magnetic sector actually works. So we would have here an ion source region. This is where our positive ions are formed. And then these will be extracted from the ion source by a lens system, meaning that the ions will move in a direction upwards here in this schematic. And then the reason why it's called the magnetic sector field is because it will enter a region where a magnetic field is applied. This is described here by this B. And what will happen is when a charged particle enters a magnetic field, it will go onto a circular motion. And this is dependent on its mass. So the radius of this motion will increase or decrease according to the ion's mass. So what is actually a rather simple principle, because if you put a slit in the middle of this circular motion, you can pretty much filter out everything that you don't want to see, and you can let through what you want to see. In our case, this is a mass to charge ratio of 2, which is hydrogen. So when the ion has passed this slit, it will go here to a suppressor lens, and then it will be registered by a detection system. Regarding sample conditioning, we have 2 major concepts for this. So this one that you see here, this is the ICE, so the internal combustion engine HSense's sample gas inlet system. You see here there are quite some compounds implemented. So we would have a water trap, then we would have a filtering system, and then we would have our gas inlet system, which will introduce a small proportion of the gas into the measurement cell. The reason this is made this way is because on the one hand, we have on ICE, we have, of course, we have moisture in the gas, but also we have the possibility of having particles and soot and dirt, which we don't want to have in our vacuum chamber. So what we would do is we would have some sort of line on the sampling port. The gas will be attracted by a pump. It will go through the gas cooling system where the water is removed. Then it will go further on into the filtering system where particles are removed. And then the purified gas is then introduced into the vacuum chamber where the analysis will proceed. And here you also see that the actual amount of gas that goes towards the measurement cell is very small, and most of it will just be pumped to the sample pump in a bypass arrangement. So most of the gas will go to the sample pump, and a small proportion will go into the measurement cell. So what are the specs that we have on these instruments? So the principal type of analysis, as I've already mentioned, is a magnetic sector field mass spectrometer. We are using electron impact ionization in order to produce the ions that we want to see. This instrument has a very limited mass range, so we can analyze masses 2, 3, and 4 with this type of instrument, meaning that the accessible compounds are mainly hydrogen and helium. The detection limit for hydrogen on these instruments is 1 ppm, and the detection limit for helium is 20 ppb. And for these types of inlets, so we have the ICE inlet that we have just seen. The pressure ranges on the sample point can range from 270 millibar absolute to 2 bars absolute. And the gas inlet pressure for the fuel cell type gas inlet is again from 270 millibar absolute up to 2 bar absolute. And on the anode side, we can do higher pressures. So this is since the The anode side of a fuel cell is usually at an elevated pressure. The gas inlet is able to cope with 1 bar absolute up to 6 bar absolute. Measurement ranges are variable. So this is something that we can very much custom customer needs for. Our standard measurement ranges for the HSense instruments are 0 to 10,000 ppm and 0 to 50,000 ppm on the low range. And for higher range setups, it's also possible to have 0 to 10% and even up to 0 to 100%. This is something that we can very much customize. So if there are special interests to have a setup which is not covered here in these standard setups, this is something that can be ordered with us, and we can adapt the instrument to suit the customer's needs for the measurement range. What are the key benefits? First of all, the use of these magnetic sector fields, these are very, very stable instruments. So the concentration or sensitivity drift of this instrument is almost non-existent. Depending on the gas inlet, you can have response times down to 100 milliseconds T90. This is always something that is connected to the type of gas inlet. So for example, the ICE gas inlet is slower due to using the gas cooler and filter, and the fuel cell gas inlet is faster because it's a direct coupling without any dead volume inside. The instruments have a very high degree of linearity. So we have, according to our specs, throughout the complete measurement range, we can hold an accuracy of 2% of the measured value, precision of 3% of the measured value, which is very good. You can use the instruments for diesel, gasoline, and CNG engines. This has all been done with customers that we already have in the field. And for those of you who have the need of higher level of automation, there are multiple software interfaces available, like AK, Connect, or various kinds of field bus interfaces, should the instrument need to be integrated into a fully automated environment. Our software we are going to see in a minute when we do the live demonstration. So you will hopefully find it as user-friendly as we wanted to make it. And also the maintenance level of these instruments is rather low. So what we recommend is typically preventive maintenance once a year. That's pretty much it. So I've briefly mentioned before some prerequisites which we require from customers that need to be present on an installation site in order to operate the instrument according to our needs. What we need is zero and span calibration gas cylinders. I will show this just in a minute. So the instrument can be calibrated by the customer according to certified calibration gas cylinders. So we typically use nitrogen as a zero gas and a certain known concentration of hydrogen in nitrogen in order to do the sensitivity calibration of the instrument. What we typically do not provide with the delivery of one of these instruments is piping and tubing from the sample points. So we have our sample lines, but the connection to the actual sample point needs to be prepared by the customer. And also what is usually provided by the customer is external controlled PCs. This is not something that is within the standard delivery of an instrument. So here I'm gonna just show this briefly because we're gonna do this live in just a minute. So this is a picture of our software. I will go over this in just a few seconds. Maybe this is something that is interesting for specs. Again, so this is a linearity curve for an HSense analyzer measuring concentrations up to 100%. So we see here the coefficient of determination is pretty much as close to 1 as you can get. Slope is also only 0.1% away from 1, and intercepts are also very good. So this is the amount of linearity that you can expect from an HSense instrument. We also have done this in the low range. So this would be going down from 1500 ppm down to 0. And again, you see by selecting the correct measurement range, you will have this high degree of linearity throughout the concentration ranges that the instrument can be applied to. This is one of the typical curves that we would see when we do a so-called T90 time test. So what is happening here is we are gonna run nitrogen on the instrument, and then we're gonna immediately switch to a 100% hydrogen concentration. So this is the signal curve when the instrument responds to a large jump in hydrogen concentration. So this would be the way up, and then we are running 100% for a while. And then this is how it would look like if you go into the other direction. And here, this is something that is also customer motivated, because on the fuel cell system, so what we see here is the fuel cell anode system running on 100% hydrogen. And what is happening here is we are changing the pressure of the sample point in a very short amount of time, from 0.5 bar gauge to 3 bar gauge. So customers were interested on how the instrument responds to an abrupt pressure change on the sampling point. And as you see here, we have lower than 2% brief deviation when the pressure is increased, and as well when the pressure is decreased. So this is something that can be expected from this gas inlet, that it is very stable also under fluctuating pressure conditions. So, and we're already at the end of the presentation. So this is something that I would suggest you can go through if it interests you. So this is a list of all the reference customers that use the HSense instruments. So that the list is rather expensive, reaching pretty much throughout the world. And yeah, this is one of the instruments that is very valued by our customers. And I thank you very much for your attention. And I don't know if we should do a little question and answer session right now, if there are, and then we will go to the live demonstration. Thank you very much.
Good afternoon. I am Pramod from Reliance.
Good morning. Oh, good afternoon to you.
Good morning to you. You're right. Your instrument is you showed. Can you go to the second last slide where pressure change was presented?
Yes, just a second. Second last slide.
Yeah, I mean previous one. Yeah, this one. Yeah.
This one. Yeah.
Yeah. So you are talking about the purity measurement. So at the last, when pressure was decreased from 3 bar to 0.5 bar. So what was the label? This is the graphical representation. The moment we are going to the absolute numbers, what was the numbers? Those numbers.
So what was done here is, so we are running 100% nitrogen in this stage at 0.5 bar G, and then we're switching to 100% hydrogen. So you see here, so the ion yield in volume percent is the actual hydrogen concentration. And what has happened then is we are still on 100%, but we are increasing the pressure on the measurement point from 0.5 to 3 bar. And so this is to demonstrate on how the concentration of the instrument will react to a very abrupt pressure change. So we see here what happens is that in the instrument, there is a secondary regulation circuit which will regulate the gas flow into the instrument. And this is the amount of regulation that you would see when you change the pressure on the measurement point. So you would have like a below 2% short increase, because this is when the pressure goes into the instrument, and then this is when the regulation kicks in and stabilizes the signal to the 100% value. And the same thing would happen when you go from 3 bar abruptly down to 0.5 bar. Then the instrument will regulate the gas flow into the measurement cell, therefore keeping the actual real concentration at the same level.
Okay, okay, very good. Just I wanted to know those numbers. Anyway, it's all right. No issue. My second question is, your instrument can be, is it online analyzer, and can it be used at the multiple location, multiple sample point? The same instrument can be used at multiple sample point.
This is something that can be implemented, yes. So you would, there needs to be some sort of sample switching system in order to do this. So we have, on the instrument, we have one sample inlet port. So if you have multiple sample locations, there are typically there are these rotary valves with 16 ports where you can supply gas to, and then switch the different locations. So it's, in principle, you can always measure only one location at a time, but you can switch between different locations using a sample switching system.
Okay, I believe that it must be ATEX certified, intrinsically safe to use in the operating area, or does it need analyzer house?
I'm sorry, I did not catch the last point. Could you repeat?
I am talking about the safety of the instrument. Can
Yes.
this instrument be used in the operating area? Is it intrinsically safe? That means ATEX certified?
Yes, of course, yeah.
Okay, okay. And my last question will be, how frequently, you rightly said there is a more stable this, that. How, in the true sense, how frequently it needs to be calibrated? And how many calibration guesses will be needed to make sure that instrument is giving linearity, like 2-point calibration, 3-point calibrations?
So
and for all component we need to calibrate then at one go, or every time we need to calibrate one component at each time?
So first answer is we are using 2-point calibration. Since as you see, the degree of linearity is very, very high. It doesn't really matter if you calibrate it at 10 volume% or 60 or 100. So what we would need is we have a zero gas in order to establish the background. And then we have somewhere within the measurement range a certified concentration from a calibration gas cylinder can be used in order to calibrate the instrument. So it's for the HSense, since we are only measuring hydrogen, you would need 2 calibration gases in order to do the calibration of the instrument. As far as frequency of calibration goes, this is pretty much something that we can only suggest. So the calibration typically takes roughly 5 minutes if you have both gases available. So what I recommend to customers, if you have crucial measurement tasks, it always makes sense before you do a run on an engine or on a fuel cell. I would do a calibration before the run, since it doesn't take a lot of time. And then you are safe for the next at least 8 hours that you have reliable results from the instrument.
Okay. Okay. And for the calibration, each component needs to be calibrated?
There is only one component. There is only hydrogen.
Okay, okay. We need to calibrate only hydrogen.
Exactly. This instrument is mainly used for hydrogen analysis. So
that's what I'm saying. Contaminants. The moment we are talking about hydrogen fuel cell quality, ISO 14687, there are certain other contaminants. So, I mean, these contaminants will be measured by this instrument or not?
No, this is a different kind of instrument. So today, this instrument is called HSense. So this can measure the hydrogen concentration. On the ISO 14687, there is contaminants to be measured in hydrogen, not the hydrogen itself. So this is an instrument that is called Hydrogen Sense, but it's not really the topic of this meeting today. So okay. Maybe we can organize something similar to this for this other type of instrument. So now, since I'm standing next to it, you can pretty much get an impression of its dimensions. So it's a It's a box of about 70 kilos coming in this red housing. This one is pretty much the more uninteresting part. So this is just the label of it. And the interesting part for you will be when we rotate it around. So since we're using turbo pumps, when the instrument is running, you need to move it very carefully because there is a turbo pump rotating at 1500 hertz inside. So any kind of angular momentum that you put on the instrument is not really appreciated by this pump, which is why we usually recommend for the customers to place the instrument at a certain location, and as soon as it is in operation, you would not move it until it is switched off, the turbo pumps have run out, and then it's safe to move again. This instrument is an internal combustion engine type of HSense. This is usually for us immediately to be seen because we have here this big filter unit that we have seen before in the schematic presentation. So as you see, this instrument is already running. This is one of the most important points with mass spectrometers. So it is not something that you switch on for half an hour and then switch back off again. There's a vacuum system inside which takes a certain amount of time to be pumped down, meaning that when we operate these instruments, we usually switch them on and then they keep running until you really know, all right, I'm not going to need it for 1 week. But if you need it every day, the instrument keeps on running and the vacuum keeps on pumping. The reason for that is that background values for the hydrogen signal will need a certain amount of time when you freshly start the instrument. So we are usually recommending with HSense instrument, it should run for at least 3 to 6 hours before measurement results will be valid. That's also the reason it doesn't make sense to switch it on and off every day because it should just be running so that it's always ready to be used. So in order to operate the instrument, what do we need? We see here, we have a power connection and power switch. So this would be, in this case, it's a 220 volt, 50 hertz power supply. And the main power switch will be flipped in order for the instrument to start. The next thing that we have here is we have an Ethernet connection. This is what I've also mentioned briefly before. So this Ethernet connection, in our case, will go into our company network. And then we have our control PC where I'll be sitting, which is in the same network. Therefore, the instrument can be accessed pretty much from any point as long as you're in the same network range, which is rather convenient because if the instrument is standing, I don't know, a few hundred meters away at a test cell and you want to have a look at it, you can also do that from another building as long as you have a network connection to the instrument. The next thing below here, this would be the RS-232 port. So there's also a possibility to control the instrument via AK protocol over a serial interface. This is also standard on this instrument. We have here all these plugs, these BNCs are analog in and output BNC ports. So you can also supply signals into the instrument or take the signal of hydrogen out on one of the analog out ports in the form of a voltage between -10 and 10 volts. The more interesting connections then come here. So we have four connections, which all concerned with gas transfer. So the rightmost one, this is the sample inlet. So the sample inlet will be the one that you use to attract the gas from your measurement point. So this is where the gas goes in. Then we have the two upper ones are the so-called sample out and vacuum out ports. So these are both gas outlet ports. This is where you would connect the lines to your exhaust system. So the sample pump will attract gas through the sample inlet. Inside, the analysis will be done and all the gas that is not used will be put out on the sample out port. And the whole vacuum system will vent the gas that is drawn from the high vacuum through the vacuum out port. And the last one down here, since we have already seen that we have a gas cooling device integrated into the instrument here, this one is a liquid out port where the condensated liquid from the sample gas will be provided, and basically you would just connect a small hose there and a small glass or something where the liquid can be drained, and so it doesn't fall on the floor. Then the last connectors that we have here are the calibration gas inlets. So you will usually have your sample gas port will be connected to your measurement cell or to your engine or to your fuel cell. So you need some way to provide the calibration gases without always having to remove the probe from your measurement point. And that's why we have here on the HSense 3 calibration gas inlets. These are labeled with inert, Cal1 and Cal2. And this is where you can provide the calibration gas cylinders, which we are going to do in just a minute. And you can switch between these inlets and the sample inlets via the software. So you don't need to disconnect anything from the sample point. And this can be easily done with our measurement software. And here, okay, the filter system is something specific to the ICE version of the HSense. This is also very simple, since filters usually after a certain amount of operating time will get dirty because there is soot in the measurement gas. And this is a very simple system. You can just unscrew this glass, take the filter out, put a new one in, rescrew the glass, and then you're good to go for your next measurement project. Okay, so I will leave the camera on the instrument and right now just give you a brief impression on how the software looks like. The software that we use to connect to our instrument is called V&F Client. So basically this first window that you would get is a list of all the connections that you have saved. So if you own multiple analyzers, you can access all of these analyzers with the same piece of software. And in this case, this is the serial number of the instrument that we see on the camera right now. You would enter the IP address of this instrument, and then you can click connect, which would then open the measurement window that we have briefly seen on the presentation just before. So I will now share only this part. So maybe a few words to the software. We have a few main components that are displayed when you connect to the instrument. So you would have this upper leftmost part. This is the instrument control. So we have here general instrument control. So we can put the instrument to measure standby and also do automatic calibration with this point. And there is also the option from this window to save the data directly into a text file if you don't have any connectivity options. So if you're not using AK protocol or if you're not using the analog out ports, you can also save the data directly onto the computer where you are working at. For the HSense, this part of the software usually displays all the molecules that are being measured. Since we are on an HSense instrument now, there will usually be one molecule here, which is hydrogen. We have here on the top this drop-down menu. This will allow you access to the different kinds of measurement methods. So we see here we have one method going from 0 to 50,000 ppm, and we have one method going from 0 to 100 ppm. Then the next thing is we can control the sample inlet. So we will see right now we are running the instrument on an inlet which is called sample with pump. This means that gas will be drawn to the port that is labeled sample on the instrument using the sample pump. And this would be the standard gas inlet that you would use when you want to draw gas from your measurement point. When we open that, we see we can also switch to the calibration gas inlets here. So here we have the inlets are labeled inert, Cal1 and Cal2. So once we switch to one of those, we're going to look at that in just a minute. We will see that gas is no longer introduced through the sample inlet, but we will use the gas bottles which are connected to the calibration gas inlets. The last thing we have here, as you see on HSense, is this part is grayed out. So what we see here is the sample gas inlet pressure into the high vacuum chamber. This is something that is adjusted by us here at when we produce the instruments, and is fixed according to the measurement range that is required from the customer side. And the main part of the software is pretty much data display. So what we see here is we have a graph. Right now, of course, since we are measuring ambient air, there is not a lot of hydrogen there. And we will see the graph move as soon as we go to a different kind of gas, which we have here. And what I would like to do briefly is I will stop this one and go back to the video. So what we're going to do first is we're going to connect two gases to the calibration gas inlets. So this is like a quick connection system. So you just put it in and it will interlock by itself like this. So now we have connected nitrogen to inert and a 1% of hydrogen calibration gas onto the Cal1. Okay, so I'm going to have to share my screen again so that you can see. Okay, so first things first, maybe saving data is something that is necessary here. So what I would have to do is I'm going to go into the options of the method, and I can choose a directory for me to save the data in. So I will just use my desktop. And I will give the file a name. And then I will confirm that with OK. And as soon as I push here on the save button, you will see, all right, the red light goes on, and also we see immediately the file is created. So what's happening now is that the values from the measurement will be recorded into this file. And so now what we're going to do is we're going to have a look what's happening when we switch to the inert inlet. So what we should see is here we were running around 6 ppm of hydrogen in our ambient air, and now we are providing 100% nitrogen. So this level should go down. I can change the scaling for this molecule. You see right now, this one is scaled up to 50,000 ppm. So we are not going to see a lot because the signal is very low. So we're going to go down to 50. And so here is, you see what's happening. So this was the measurement curve while we were measuring in ambient air. And this was when we changed to nitrogen. Now I'm going to change the scaling again, because the next thing that we are going to do is we're going to look at a calibration gas. So what I will do is I have attached the calibration gas to my Cal1 port. So via the software, I will switch to this calibration gas. And so we see here, this is how the gas changes. So now we are providing 10,000 ppm of hydrogen to the instrument. And of course, it will read that. And when we go back to the sample with pump board. So we were going to run ambient air again. We should see that the measurement value pretty much immediately decreases back down to the low level. So there's also that there are multiple ways how this instrument can be calibrated. As far as we see here, all right, of course, since I have done the calibration this morning, everything is all right. So we are providing 10,000 ppm, we are reading 10,000 ppm. If this is not the case, so maybe recalibration hasn't been done in a while, I can simulate this briefly. I will just change the sensitivity value to something that is not true. So what I would do is, first step, I will go to the inert inlet. So this is my background gas. This will give me an impression of how much signal do I have when there is actually no hydrogen there. So this is the value that I would calibrate for the background. And this can be done either automatically, this would be with the calibration routine. And for today's purpose, I'm going to show you the steps manually. So this is also possible. So for example, right now, I'm running my 100% nitrogen sample. And what I would do is I would right click the molecule and I would get a menu where I have calibration options. So the first thing to understand is when you do manual calibration, you will always have to run the calibration gas, which corresponds to the step that you want to do. So I'm running currently up here, I'm running inert. So this is my background gas. So the instrument will always use the most recent measured values in order to do calibration. So it will measure the 100% nitrogen. And what we are going to do is on this stage, as soon as we click background calibration, you see right now we have an offset value of 5 ppm. When I go to background, we will see that the instrument will readjust itself to close to 0 value. Yeah. Also for your convenience, when you are saving data, you can always write notes into what you are currently doing. So for example, here did a background calibration. You see, this is just a marker in time, a piece of text that will also be saved in your save file. So in order for you to keep track when you're looking at these data later on, what you have done. And the next step would be is I will go to my calibration gas with the known concentration. So in our case, we have the inlet Cal1 for that. And we see since right now I have changed the sensitivity value of the instrument manually. So we see now the instrument is not displaying the correct value. So this is a gas which contains 10,000 ppm, and currently the instrument is reading at 23,500. So what we would do is, again, we see that the signal stabilizes very fast. So we want to have a stable region. So these last measurement points will be used to do the calibration. The manual way to do this is similar as before. We would right click, we would go to calibration, and now we would choose spun calibration. So this is in order to determine the sensitivity. Of course, now the instrument doesn't know which type of gas is connected. So I will have to tell the instrument the current gas that is running has 10,000 ppm of hydrogen. And as soon as I confirm that with OK, we will see that the instrument will readjust its value. Can change the scaling back down to 20,000 that we had before. So now we see we're back to the correct value. And as soon as we go back to sample with pump, we are drawing in ambient air, which is of course at a much lower value. Okay, so I will just briefly stop the sharing again so that you can see the camera in full screen. Because the next thing that we are going to do is we're going to attach a a sample line and a small experiment where we can supply different hydrogen concentrations via the sample port. So in this case, since we are running pretty much on dry gas, we are going to use the most simple sample line that we can get, which is just a piece of 1/4 inch Teflon. And what we're going to do is we're just going to attach that to our sample line inlet. So this is where the gas for analysis during sample with pump will be attracted. Usually these switch lock types of connectors, you just tighten them with a wrench, not too tight. And here we have a small measurement chamber. You see, it's actually a very simple design. So we have 2 inlet ports. This is where we will connect our nitrogen and hydrogen calibration gas. Maybe put it a little bit further. Then we have 1 port that we are going to use to connect the instrument. And then we have 1 overflow port where the gas can go outside. So what we're going to do is we're going to take the other side of our sample gas line. This is this one. And we are going to attach it to the chamber. Again, tightening it, not too tight. Now we're pretty much going to check. So we're going to take the gases that we have just used for calibration, and we are going to attach them to the chamber like this. You see here we have 2 needle valves, which allow us to open up each one of these inlets. I'm sorry, I'm just in the way, like that. So we can see, all right, when we put nitrogen, we should see 0. When we put only hydrogen, we should see the 10,000. Then we can do also some intermediate states where we have a little bit of hydrogen and a little bit of nitrogen to produce different concentrations. Okay, so I'm gonna share my screen again so that you can follow on the viewer, sorry, on the client. Okay, so let's have a look. So I'm gonna open one of these needle valves right now. The gas flow through these valves is rather low, and the volume here in this chamber is around about 1/2 liter. So don't worry about the slower response times. This is mainly due to the real hydrogen concentration is actually rising slow. So it's not an issue of the instrument, it's an issue of the measurement chamber. So as we see here, this would be the same gas that we have just used for the calibration on the calibration gas inlet. And now we are running it through the sample inlet of the instrument. Now we're going to try the other way around. So I'm going to close this one and open the nitrogen one. Which should lead to us getting a value again close to 0. But now we're going to try to produce some intermediate values. So I'm just going to open the hydrogen calibration gas a little bit. So now both of the gases will go into the chamber. They will mix in the chamber and then produce a certain amount of hydrogen concentration, which of course should actually be lower than 10,000 ppm. And this is pretty much what we see here. Of course, I don't know the concentration currently myself because I don't know the 2 flows, but it's just to give you an impression of how the instrument reacts. So next step, I can open the hydrogen side a little bit more, maybe close the nitrogen side a little bit, which should lead to an increase in the signal. Maybe even a little bit more. I'm closing the nitrogen, which should again lead to a increase of the signal. I'm going back down to 100% of nitrogen, so we should see that the hydrogen signal decreases. Let's go back to another high flow on the calibration gas and low flow on nitrogen, which should produce a higher hydrogen signal. Okay. Back to full on calibration gas, so we should read at the 10,000 mark. So this basically, this small experiment should give you an impression on how this actually looks like. So the instrument will draw gas continuously from this chamber, do the analysis, and present the data to you in pretty much real time on your screen. I'm gonna flush the chamber with nitrogen again, so you don't have any remaining hydrogen inside. Which of course should lead us to getting a reading close to 0. Okay. Since we're done with that, we can take our gases and put them back to the calibration gas. So as you see here, data in this window is buffered. So right now we are displaying a time range of 5 minutes. This is something that can be set up here. So if we're interested in something that happened a little bit longer ago, we can just change the time. This is where we have more of the data displayed. Since now this small chamber demonstration is over, we can also have a look at the signals that we have just saved. Might be interesting to some. So we're going to do is we're going to stop this saving process. So we see here the red light is still on. So we're going to stop that. Now it's turned to white again. And maybe if you're interested in that, the way the data is saved is actually plain text. So what we see here is we have timestamps and measured values. This is how the data files are stored. So it can also easily be imported into different kinds of software like Microsoft Excel or Origin or MATLAB, whatever you are using for data evaluation. But we also provide a small piece of software. Sorry, just need to make that a little bit bigger. Where you have a similar impression of what we just had in our client measurement software. And this is what the software previously was called History, is now integrated in the client system. And this will also give you an immediate graph and the possibility to do simple statistical evaluations for the measurement curve that you have saved on the instrument. So there are some style and axis possibilities to define. So I'm probably just going to show some points so that the line gets a little bit more visible. What you can do here is you can zoom into certain areas where you have measured something. So for example, this was the part of the measurement that we did on the small chamber. And maybe, for example, we want to know the exact concentration of hydrogen that has been running here. We can go inside. So these would be all the single measurement points throughout this phase. And as you see here on the left side, we have some basic statistics that we can follow. So we would know is the average value of these measurement points is 5257.1. And we have a standard deviation of these measurement points of 14.8. And it would also give you a minimum and maximum range so that you immediately know what measurement results were going on throughout this phase. Usually we recommend always, if you do something like this, if the process is not very much transient, use a few values to average over, because that will give you a more reliable actual measurement value. So this is also something that comes with our software package. It's pretty much a very simple piece of software to do some basic evaluations. Typically, as soon as you're going into fully automated mode, then this will be taken over by some sort of computer program that does this automatically. Okay, so this was pretty much it for a first impression on the HSense analyzer. So I would encourage everyone who still has questions to let's have another session of about 15 minutes for Q&A. And so far, I thank you all for your attendance and for sharing your time with us. Please, if there are any questions, go ahead.
Hi.
Hello.
So how many readings can be recorded in 1 second?
The most that we can do is 20 hertz, so a cycle of 50 milliseconds, 20 readings per second.
Okay, okay. And this data can be imported to the test bench software automation system.
Exactly. Usually when we are working with test benches, we are using AK protocol, which is a driver that is installed on the test bench, and this will just poll the instrument for new data.
Okay, yeah. Thank you.
Any further questions from one of the attendees?
Hello, this is Gaurav here.
Hello.
Yeah. Actually, I just wanted to understand: is there any external equipment being used to find out the to conduct the linearity of this system?
Yes.
In order to ensure the accuracy of the measurement.
Exactly. This is something that we go through here when we build the analyzers. There is a verification process in order to guarantee that linearity and accuracy and precision and all these parameters are correct for the instrument. And this will also be delivered in the form of an analyzer report for the instrument.
So whatever costing you have put some time back for the instrument, it will include this the gas divider, I mean to say this linearity equipment.
Exactly. This is what we do for each and every instrument that we build. So we are when the instrument arrives at my department from production, what we are going to do is we're going to set up all the ion optics and like lots of parameters to be set up, and then we are running a measurement protocol. So we are checking the instrument for linearity, stability, accuracy, precision, T90 time, and depending on the application, additional tests can also be done, and depending on the customer's needs.
I just mean to, I mean, I wanted to understand is like, this is, I mean, separately, it's a separate system or it is embedded inside the same
Oh,
system?
so sorry. No, it's a separate system. Yes. So we are
Okay,
using
thank you.
we are using gas dividers that are separate instruments to provide gas mixtures to the instrument, to the HSense instrument. Yes.
Okay, thanks.
No problem.
So where is the option for the leak check process in this instrument?
Leak check process is actually not really necessary because the whole system runs on below ambient pressure. So any leak that you would have goes inside of the instrument. And that is something that we very diligently try to avoid when delivering these instruments.
Because there may be a leakage from the sample point up to the instrument or even inside the instrument. How would we detect that if we don't have any leak check process?
The way you would detect that is to you could do a helium spray test. So you would provide the instrument with nitrogen from the sample point, and then set up a method to measure helium. And if you spray the instrument with helium and you see excess signal, then this would point to a leak.
So it's going to be a manual process, right?
Yes, exactly.
I think it's better to have the function that happens through the system.
Yeah, that's something that we would have to develop. Currently, we don't have something like this in operation.
Yeah, right. Okay.
So what are the routine checkups that are required for this in daily operation?
It's pretty much doing the calibration with calibration gases. So if you the instrument will there are loads of parameters which are monitored inside. So there's like different types of pump control, pressures, temperatures, and anything that is out of range will produce an error message. So there is a yellow or a red exclamation point which will appear in this region when there is something wrong with the instrument. So like a visual inspection with this program would be good, because then you see, all right, there's something going wrong and I need to take care of it. And apart from that, when everything is running fine, it's mainly just to do the calibration with the calibration gases.
Mm-hmm.
Well, one more thing, is there any purging option for this system so that, you know, clean up frequently? Because we will be continuously testing the system. Maybe after some time we have to clean this, the complete sampling line. So is there such options given for purging the system?
Usually the parts of the instrument that become dirty, as you've mentioned, are typically sampling lines. We don't have an option to purge out this kind of contamination, because the soot contamination from typically combustion engines is not something that is easily cleaned. What we usually do is we have heated lines which have a Teflon center, which means that after a certain amount of operation, you would detach the heated line, remove this Teflon center, put a new one in, and continue on measuring. So like having a purging process or a cleaning process during operation is not currently installed, no.
No, I'm not telling during the operation. I mean not during the measurement. I'm telling, is there any separate purging option so that we can keep the system healthy and keep clean? No, we can measure with the hygiene.
I'm not quite sure if I understand the question correctly. So when you are measuring on a port where there is particulate contamination, you still want to measure. So that is something where the components of the instrument up to the filter will take a little bit of dirt. And do you mean while you are not really interested in the hydrogen signal, you want to have a purge option to not get the gas from the sample point? Is that what you mean?
No, actually, I just wanted to say that we will be continuously measuring the hydrogen content from the engine exhaust.
Yes.
But after the operation, after the measurement,
Yeah.
there will be a possibility that water content or maybe some dirt or dust, or we may be even using some impure gases which may have some dirt into it, and that may be clinged into the sampling line. So
Okay.
this needs to be cleaned right all the time. Otherwise, you may get the measurement accuracy you may not get because of the dirt and dust in the line, or you may not get a sufficient sample pressure when you are measuring it. So in order to avoid those things, there is a option called purging in most of the exhaust analyzers. So I was just comparing in that way, and I was asking you that is there any option given in any such kind of option given in your system?
Currently, no. This is it's a manual process. So if the sampling lines, or let's say the things that can get dirty is the filter and is the sampling lines. From there on out, the gas is already clean. So on the inside of the analyzer, you don't have to take care of that. On the outer parts, like filter sample lines, this is something for hydrogen. What you're saying is very true for other compounds. For hydrogen, the dirt is not really too much of an issue. The issue could be that if the sample line is so dirty that it clogs so that no gas can come through, then yeah, you will not get a response from your process. And this is the point where the sample line needs to be cleaned. But we don't have a back purge option where you can just blow out the dirt from the sample line after a long operation. So this is something that is like a preventive maintenance task, you could say. Like when after measuring for 1 month, you should do a clean check on the sample lines.
Okay, so mostly the filters whatever been placed in the line.
I'm sorry, I've just lost connection a little bit. Could you repeat the last question, please? I'm sorry, I don't know if I can be heard, but there seems to be some connection issue. Could you repeat the last question, please?
Yeah, I'm sorry. I mean to say that the filters, whatever are there in the line, that is sufficient to clean up the system as of now.
Yes, of course. That's why they are there. Yeah. So all the particulates will be trapped in this filter, so that the gas, that this dirt does not get into the downstream gas inlet system. So a vacuum chamber needs to be clean, and also the interior piping is usually always clean. But you're right that there needs to be some sort of maintenance interval, because if the filter is really loaded and it breaks through, then you can get an issue. So that's why we have this viewing glass. So if you see that the filter is getting dirty, then it makes sense at the appropriate time, when the instrument is not currently measuring, to just do this quick maintenance procedure to exchange the filter, and then you are on the safe side again.
Okay, thank you.
No problem.
Hello.
Hello.
Yeah, what is the frequency of changing the filter? Is it daily basis, or any time frequency is there? And then is it cleanable or use and throw type?
I'm sorry, the last part, I did not understand the last part of the question. Could you repeat that?
No,
please?
that filter, we can clean it and use it again, or is it use and throw type? Filter type.
It's usually throwaway.
Okay,
So
then,
I have not heard from customers that actually clean the filters and reuse them. So it's just a small filter tube that you take out, throw the old one away, put a new one in. And the time where you need to change it depends pretty much on operation. So I would probably, if you're really going 16 hours a day, I would change it once per week. If you're going less time, then the filter may last a longer time.
Okay.
Any further questions from the attendees?
So the instrument requires power source and calibration gas and operating gases. That's enough, right? Or is there any compressed air source? I mean, compressed air is also required.
No. It's only the gas from the measurement point, so the gas that you want to analyze, and the calibration gases. Okay.
Then one more, that heater line connection, how it is? It's external source or is it along with the device?
So for heated lines, we also have multiple options. So for example, here you see that the heated line is supplied by the instrument itself. So you have a temperature controller and the connection to the heated line coming from the instrument. This is, you could say, this is the little bit more expensive version, but you can also have the heated line. So this can have the controller integrated on the heated line, and then you just plug the heated line somewhere onto a power outlet. This is also possible.
Okay, this is a fuel cell, no? Fuel cell analyzer.
This would be the fuel cell analyzer, yes.
For ICE.
So we see here for ICE, the analyzer itself does not come with a heated line per default. So this is something that is an extra. On the fuel cell system, we provide the lines as well, but this depends on your needs, how long the line needs to be. We can provide it, but if you choose to have one still on your site, or if you want to buy it yourself, you can just connect it here. And of course, then the supply for the lines is within your domain, so you need to take care of it.
Well, one more question. I just wanted to know, is there any way to find out the response time? I mean, when from the engine exhaust, the gas has been collected to reach that exhaust gas to till the system. How much time it takes? Because it is very important for us to, in emission test cycles and all, to see at the particular time, I mean, in what time it is reaching to the analyzer. From there, the measurement starts. So
yeah, this is typically done experimentally outside. So you would have your analyzer and your sample transfer system. So be it a 3 meter or a 9 meter line, and the run time of a signal change on the sampling point is simulated. So you would just connect the calibration gas to the front of the instrument in a bypass. And then you would take the time that it needs until you switch the gases to some hydrogen concentration and until the instrument registers it. And this is usually a delay that is implemented into the test bench. So this is what, as far as I know it from our customers, how this is done. Okay, so I think we've covered quite a lot today. Again, I would like to thank all of the attendees for taking the time and accompanying us on this small demonstration of the HSense unit.